Hi everybody, welcome to another video in Calculus 3, partial derivatives. This is one of the most important sections in Calculus 3. We study about derivative of function of multivariable. So pretty much we will have a function of two variables, could be more, but keep it basic, two variables. Right, and the way we define the derivative is actually only partial derivative. So how do we define that? So there are two variables, x and y. We're going to keep one of them constant. So let's say we fix b. This is the vertical line plane, y equal to b. So we're going to keep y as constant, y equal to b, and b is constant. So if b is equal to constant, we're talking about this plane. This is the plane y equal to b, and it is intersection to the graph of the function. And the intersection is this part of the graph. It is a curve. And on that curve, we can define the derivative as the slope of the tangent line to the point. So this is just like count 1, but we define like this. And once again, we're going to keep the second component, the y coordinate, to be b, which is constant. So we only change in x, and define this just as different quotient, and take the different, the h go to 0. So this is exactly like calculus 1, but we just keep the y as a constant, and with that we define what we call is the partial derivative with respect to x, where we let y is a constant. So when we let y be a constant, what we will have when we define derivative is partial derivative with respect to x when y is a constant. And likewise, we do the same thing. We can let x be a constant if we let x be a constant, and there is the intersection of the graph and the plane x equal to a, sorry, and then we define the slope of the tangent line. And the same way, if we have fixed, if x is constant, then what we have is partial derivative with respect to y. So bottom line, that's all we have. If there's two variables, x and y, we have partial derivative with respect to x and partial derivative with respect to y. Right. Now the proper definition. The partial derivative of f with respect to x at the point a and b is given like that. So once again, this is with respect to x, so we're going to keep y as a constant. And we treat y as a constant. And derivative with respect to y, we're going to keep x as a constant. And because just like everything else, if we define the derivative in terms of limits, the limits must exist. Right. So simple enough, right? Treat x as a constant, we have derivative with respect to y. Treat y as a constant, we have derivative with respect to x. Right. Before we actually go to do some example, just look at a different notation for derivative, and there's some more than just this, but we will use f sub x for partial derivative with respect to x, or we're going to write like this, and that we just call the partial derivative So we do not use d. The df over dx, that is the derivative, partial derivative. We're going to use that weakly d. Or we can write like this too. So either we use a subscript or we use that notation. We're going to use both of those. Right. But when possible, we just use the subscript. Right. Now, let's go to the examples. Let f of xy equal to this. Now, let's find the partial derivative with respect to x. So partial derivative with respect to x, we don't need to write xy here if the variables are clear. We just need to write f sub x. That's good enough. Okay, or x of xy, doesn't matter. Right. Now, if it is with respect to x, that means y is a constant. So derivative of x squared with respect to x is 2x. Derivative of negative y squared with respect to x, y squared is a constant, 5 is a constant. Derivative of constant is equal to 0. So that's all we have, right? Yeah. With respect to x, that one is a constant. That one is always a constant. So derivative of a constant is equal to 0. Derivative with respect to y, x squared with respect to y is a constant. Derivative of a constant is 0. So x squared, derivative of x squared is equal to 0. So we can even write like this. X squared with respect to y is equal to 0. So the derivative of x squared with respect to y is equal to 0. Because with respect to y, x squared is just a constant. Derivative of constant is 0. Right. Derivative of negative y squared with respect to y, negative 2y. And derivative of 5 is a constant. Derivative of constant is 0. So that's pretty much it. Now evaluate each derivative at the point. So we can evaluate this at 2 and 3. 3 and 2 and negative 3, meaning x equal to 2. I put 2 in for x. Or we can say like this, 2x evaluate at 2 and negative 3. So that's just 4. And the derivative of y at 2 and negative 3 is negative 2y. Evaluate at 2 and negative 3. Negative 2, y is negative 3. That's 6. Right. Yeah, so it's simple enough. Derivative, just treat the other one as a constant. That's basically it. And then all the chain rule, product rule, quotient rule, and all the rules of derivative will still be the same. Now, find all the partial derivative for this one. Since it has only x and y, so we want to just have partial derivative with respect to x, then with respect to y. So first, with respect to x, of course we can write the notation using this, or if we want to, we can just write derivative of f with respect to x. Yeah, either notation is fine, either that, or even that. There are a few more, but those are the common one. Right, now, derivative. Now we're going to treat this as a chain rule. So ignore everything inside. Derivative of sine of something is going to be cosine, right? So it's going to be cosine. I'm going to put the parentheses around here. Doesn't matter what inside. Derivative of sine is cosine of the parentheses, and then we take derivative of the parentheses. But it's unlike the derivative. This is derivative with respect to x, so we're going to take derivative with respect to x. Inside the parentheses is x and y. Yeah, so that is the chain rule. Yeah, just ignore what inside the parentheses, take derivative, and then take derivative of the parentheses with respect to x. Now, what is derivative of xy with respect to x? But it's still cosine of xy. Now, what is derivative of xy with respect to x? So think about this. With respect to x, y is a constant, right? So with respect to x here, y is a constant. So what is the derivative of a constant times x? So I'll ask you a different question. What is derivative of something like 2x? So let's say if we have derivative of 2x with respect to x, of course that's going to be just 2, right? Because 2 is a constant, so just 2. Same thing here, derivative of xy when y is a constant will be just y, because the derivative of a constant times x is just that constant, and this time y is a constant. So we're going to have y cosine of xy. Right, next, derivative with respect to y. By the way, I just switched the notation for no reason, just to demonstrate that you can use any notation. Right, similarly, but this time with respect to y, derivative of sine is cosine. And then derivative in sine, this time with respect to y. And then inside the parentheses is xy. And with respect to y, x is a constant. Right. So we still have cosine of xy. Let's put the parentheses around that. And then derivative of xy with respect to y. Once again, x is a constant. So a constant times y, derivative of a constant times y is that constant. So we're going to have that constant is x, sorry. So just have x cosine of xy, right? Because with respect to y, x is a constant. Derivative of a constant times y with respect to y is just x, just that constant. Right, next, a little more interesting. So when we write like this, x squared times e to the xy. So let's take derivative with respect to x. Once again, you can use g sub x or derivative of g with respect to x, doesn't matter. I just use randomly, just use g sub x. So when we look at this, we see x squared has x in it. That's good. If xy also have x in it, so this have to be a product rule because x show up in two different places, right? So this one is the product rule. So I'm going to write u equal to x squared and v equal to e to the xy, and derivative here is going to be u prime v plus u v prime, so product rule. So let's just say u prime v plus u v prime. So that is derivative with respect to x. Right, u prime with respect to x. Of course, we're not going to write like that because that is the derivative. Now here we have partial derivative, so it's still the same thing. We're not going to use the prime sign, but we use derivative with respect to x. Still the same thing, right? Derivative of u with respect to x, that is just 2x. That's easy. V e to the xy is still the same. U x squared still the same. Now derivative of this with respect to x. Now I'm going to put the parentheses around the exponent. So this is just like chain rule. Derivative of e to anything is the same thing. And then we take derivative of that part with respect to x. And in parentheses xy, xy. Right. So here we have 2x e to the xy plus x squared e to the xy. Derivative of xy with respect to x, once again, with respect to x, y is a constant. Derivative of a constant times x, just like this. Derivative of constant times x is just that constant. And that constant is y. And if we want to, we can factor out e to the xy. It doesn't matter. So that's what we have. Right, so that is the product rule. Right. Derivative with respect to y also the same thing. However, it's just a little bit different. That one doesn't have x in it. I'm sorry, that one has x in it, but if we take derivative with respect to y, that's just a constant. So we don't need to use the product rule when we take derivative with respect to y. But I'm just going to do that in a minute. Just do that. Same thing though. Product rule. Derivative of u with respect to y times v plus derivative of u times v with respect to y. Now we're going to have x squared. U is still that and v is still that. Derivative of u with respect to y, there's no y here. X squared here is just a constant. Derivative of a constant is 0. Because here there's no y. And derivative of a constant is equal to 0. And then v is still e to xy. So this is still 0. U is x squared. Derivative of this still the same thing as similar to that, e to something, and derivative of that with respect to y. Have xy here, xy here. 0 times anything, so this goes to 0. And then we just have x squared e to the xy. Derivative of xy with respect to y. With respect to y, x is a constant. Derivative of a constant times y with respect to y is that very constant. So we have x cubed e to the xy. Yeah, we don't even need to use this. We just go ahead and just, by the way, that is the answer. If we want to, we just say derivative here is going to be just x squared is still constant, so constant doesn't, we don't need to use the product rule. And then we have e to something, derivative of that with respect to y, and xy, xy, and then of course the same thing, x squared e to the xy times x, which is x cubed e to the xy, same thing. So we don't need to use the product rule because we don't really have the product of two functions of y. We do have the product of two functions of x, so that product rule is perfectly done there. We don't need the product rule for y because we only have one function for y. Right. Now let's go to this. Derivative of ln of x is 1 over x. Right, so we have that part done. Now this one is a little bit different, so I will rewrite what inside of the parentheses here. We can say it, the 3 is still at the bottom, so we cannot do anything with it. Right? X squared, if we want to move the y from the bottom to the top, that becomes y to negative 5. Right, that is better. Now we have derivative with respect to x, derivative with respect to y, and this is just a chain rule. So derivative, by the way, that is a terrible way to write this. Y is that, so sorry, that obviously a typo, so let's make that do something else. Of course, we still can have y equal to that. In that case, derivative is a little bit different. We're going to do that in the next section though, not here. Here we have z depend on xy, even by that. So derivative of z with respect to x, derivative of ln of something. Once again, I'm going to use the chain rule. Derivative of ln of something is 1 over that thing, and derivative of that, I should use apostrophe, but this with respect to x, so I'm going to say with respect to x. Right, doesn't matter what inside of the parentheses, it's always like that, the chain rule. So I'm going to put 1/3 x squared y to negative 5 right, 1/3 x squared y to negative 5. Right, now I'm going to have 1 over 1/3. There's no derivative here, so I just rewrite that. I still have 1/3. Derivative of x squared is 2x. The reason we just do that because y to negative 5 is still constant, so we don't do anything, just rewrite it. The only thing here, there's only x there for x squared. Derivative of x squared is 2x. Everything else is constant. So if we multiply a constant to this, we just take derivative and multiply by a constant. So 1/3 constant will stay, derivative of x squared is 2x. So multiply by a constant will not affect the derivative. Right, now let's simplify. 3 here and 1/3 here, both below the denominator, so that cancel out. Y to negative 5 cancel out, and then we have 2x over x squared which is 2 over x. Simple enough, right? Now let's take derivative with respect to y. We'll do the same thing. Derivative of ln is the reciprocal function, 1 over something, and derivative of that thing with respect to y. Doesn't matter what inside of the parentheses. Right. There's no derivative here, so I'm just going to write. And then with respect to y, that is a constant, and then I just need to take derivative of this with respect to y. So it will be 1/3 constant, x squared constant, y to negative 5 will be negative 5, y to negative 6. That is derivative of y to negative 6. Right, let's simplify. Once again, 1/3 and 3, x squared, x squared. We will have y negative 5, y to negative 6 over y to negative 5. Y to negative 6, y to negative 5. I cancel out, obviously, right? So we still have negative 5 equal times negative 1. So this equal to, when that cancel out, we have negative 5 y to negative 1. How did that work though? Let me just write this again. Y to negative 6, you can write this as negative 5 y to negative 5 times y to negative 1. When you multiply them back, y to negative 5, y to negative 1 give us y to negative 6, then y to negative 5. Those cancel out, and that's why we're left with y to negative 1. Bring it down, it becomes negative 5 over y. Right, so that's nice and all, right? But it could be even better. Let me just rewrite the problem and you will see. So that is certainly the derivative, partial derivative that we have. Now if I'm going to write this differently, let's start with the beginning. How about that? Right. This is the different solution. So let's say it alternative we can do differently. We write start from the beginning, z equal to ln of x squared over 3y to the 5th. Now notice that this is a ln of a difference. Ln of a quotient. It's going to be ln of x squared subtract ln of 3y to the 5th. I can take the 2 outside. So we have 2 ln of x. Take derivative of this with respect to x is extremely easy thing to do, right? So it's 1 over x, 2 times that to give us this easily. Now I will break this as the product. ln of 3 ln of y to the 5th, and we'll take the 5 out here. So bottom line is we rewrite the function as 2 ln of x minus ln of 3 minus 5 ln of y. Sorry, for now space there, but that function is equivalent to this. Now taking derivative of this with respect to x, 2 times 1 over x. Derivative with respect to y, negative 5, 1 over y. Because when you take derivative with respect to x, those two are constant. When you take derivative with respect to y, those are constant. So we just have that. Derivative with respect to y is negative 5, 1 over y, which is this. Right? So sometimes we write a function certainly help. You take derivative. Right. Derivative of this with respect to x and then with respect to y. Right. We can rewrite this x squared and y cubed, all of that under square root. Certainly we can just keep the square root, but usually when we have the square root or reciprocal function, we can rewrite this, so we can use the power rule. Square root is equivalent to the 1/2 power. Once we write like that, derivative with respect to x with respect to y will be easily determined. Derivative with respect to x, doesn't matter what inside the derivative of something to the 1/2. Is that something, sorry, take out the 1/2. That's something original power minus 1, so 1/2 minus 1. Yeah. And then derivative of whatever that with respect to the variable x. Doesn't matter what inside the parentheses. This is subtractor. That is the derivative of a square root of something. X squared y cubed, x squared y cubed. Give us 1/2 x squared plus y cubed negative 1/2. Derivative with respect to x, 2x. 2 cancel out, and we just have x times that. And negative exponent, I just write this first. Negative exponent, we can move that to the bottom. So we have x over x squared plus y cubed to 1/2, move to the bottom, become positive. And once again, square that equivalent to square root. So we can say x over square root of x squared plus y cubed. So that's derivative with respect to x. Derivative with respect to y, still the same thing. Doesn't matter what inside the square root, doesn't matter what inside the power 1/2. Derivative using power rule is 1/2, something to the negative 1/2. And then derivative of that with respect to y. So we have 1/2 x squared y cubed negative 1/2. And then derivative of this with respect to y, x squared is a constant, derivative is 0, derivative of y cubed with respect to y, 3y squared. The 2 don't cancel here, so we just have the 2 will stay at the bottom. That power thing, actually this is the answer. If you want to, you can just stop there. But if you want to, you can move this to the bottom. Turn to positive. The 2 at the bottom, the 3y squared will stay on top. So we have 3y squared. 1/2 is equivalent to the square root. 1/2 power is equivalent to square root. That's what we have. Right. So that is derivative. Right. So higher derivative though. How do we write that? Derivative with respect to x, and then derivative with respect to x again. So we say that, but if we just say f(x)(x), in this context, we just say f(x)(x), meaning derivative of x, f with respect to x, and with respect to x again. Now it's more interesting if we have derivative of y and then with respect to x, and then derivative of x with respect to y. Because we still say fy(x), fxy, and fyy. It doesn't matter. Like I said, in this context, that assumed to be just the derivative. Right. So it's easy enough, right? Just take derivative, and then derivative again will give us second derivative. So this is the function. Let's take the derivative. Derivative with respect to x. With respect to x though, y is the constant. So when we have the product of this, don't use product rule because there's only one x, everything else is constant. So the derivative of this with respect to x is going to be 3, that constant, x to the 4th, 4x cubed, and then that y is a constant. The constant will stay, just take derivative with respect to x, and all the constant will stay as is. Derivative of this with respect to x, the constant 2 will stay, derivative of x is 1, with respect to x is 1, and then that constant y will stay. And then 5, derivative of x is 1, derivative of y cubed, with respect to x is still y cubed, that constant will stay. So this is derivative with respect to x. Now let's take derivative with respect to y from here. Right, derivative with respect to y, we just write out 3x to the 4th because that's just a constant, don't do anything. Derivative of y is 1. To xy is derivative is 2x, is still constant, and then derivative of y is 1. So when we have a product like this where x only show up or y only show up one time, just copy all the constant and then take derivative of that particular variable. In this case is y, which is 1. And then we have 5x is a constant, derivative of y cubed is 3y squared. Right? Now let's just rewrite this. That gives us 12x cubed y minus 2y plus 5y cubed. And derivative of with respect to y, 3x to the fourth minus 2x plus 15xy squared. Right, so that's good. Now go to the second derivative. We're going to take derivative with respect to x already. Now we're going to take derivative with respect to y. Let's just do f of xx. So derivative of this with respect to x. Derivative of this with respect to x. 12 is still a constant. X cubed 3x squared. We're taking derivative with respect to x, right? In that case, y is still constant. We don't write 0 because all of that together in one term, though, right? Just like when we take in count 1, when we take derivative of 2x with respect to x, we don't say derivative of 2 is 0, derivative of x is 1, 0 times 1 is 0. This is not like that, right? We just say if this is a constant, that constant will stay, and then we take derivative of x, which is 1. So we don't take derivative of the constant multiply to it, we just take derivative of the variable. If the variable show up at one place, if we have x times e to the x with respect to x, that's completely different story. This have to be a product rule because x show up in two different places. Here, only show up at one place, everything else is constant. So constant will stay, derivative of this with respect to x is 0 because there's no x here, everything there is a constant. Derivative of this with respect to x is also 0. So that's all we have. So derivative of f(x) is equal to 36 x squared y. Now, take derivative of this with respect to x, then with respect to y. So we already take derivative with respect to x, and now we'll take derivative with respect to y. The 12x cubed here is a constant, so we'll stay there. Derivative of with respect to y is 1. Derivative of negative 2y with respect to y is 2. Derivative of that with respect to y is 15y squared. So that equal to 12x cubed minus 2 plus 15y squared. Right. I try to write a little small. Now we take derivative of y already. Now take derivative of y with respect to x. So derivative of this with respect to x, 3x to the fourth, derivative of that with respect to x. We already did it with respect to y, right? So it will be 12x cubed. Derivative of this with respect to x, 2. Derivative of that with respect to x, 15 with respect to x, 1, and y squared. So that gives us 12x cubed minus 2 plus 15y squared. And derivative of this with respect to y, and then y again. Constant, that will be 0. That constant, also 0. So if that derivative with respect to y is going to be 0, we just have this, which is 15x constant, and then derivative of y squared is 2y. So that gives us 30xy. Right. So we have 4 derivatives. 4 second partial derivative with respect to x and x, with respect to x, y, and then yx. Then we said x1 and yx kind of confusing, right? But actually it's not. Notice that those two are the same. And this is not coincident. There's a theorem about that. It said, assume that f is defined and partial derivative exists and continuous throughout. then the mixed partial derivative will be the same. So it's even more powerful than just that. You can say the derivative, let's say higher order of derivative in general, like f of x, xy, like third derivative, it's going to be the same as f of x, y, x, or f of y, x, x. So as long as we have the same number of variable, the mixed partial derivative will be the same. If we have 2x and 1y, it doesn't matter which one we do first. Which variable we take derivative with respect to first, it's still the same. Right? Or we have f, x, y, then any combination. It doesn't matter which variable we take derivative with respect to first. Now a little more advanced here, but I'm not going to focus too much on this. Say the function of two variables is said to be differentiable if satisfy this condition. If the chain in dz given by that equal to this, where we have epsilon 1, epsilon 2 go to 0, 0, as delta x and delta y go to 0. And of course, like I said, this is a little more advanced. We're not going to focus much on this. Right. And this theorem, it says that suppose a function has partial derivative defined on the region containing that, and the partial derivative have to be continuous on AB, then it is differentiable. And if it is differentiable, then it is continuous. And this theorem actually is just like calculus 1. If it is differentiable, it is continuous. If it is continuous, it may not be differentiable. And this is just an example here. It says that we have the function here. I'm not going to do this because, like I said, a little more advanced here, but just going to show that this one, I think we did kind of similar to this. We say this is not continuous. This is not continuous. I'm just going to write the sketch of what we're going to do. Limit of f of xy as xy goes to 0, 0 does not exist, because we will take the limit approaching two different paths, like we did this in the previous section. Because just consider limits from different paths. One of them is like along the x-axis. Along the y-axis. And also we did this, the power of x and y are the same top and bottom. So we can say along the line y equal to x, or y equal to negative x. Yeah, we can do, just pick two of this. If the limit show, if we can show that the limit are different with two of those, then we say the limit does not exist, and we can do that easily. Just do, I'll let you do that. And then of course we can find partial derivative. Also, like I said, it takes a lot of work, but this is an example show that the partial derivative with respect to x exists, partial derivative of y exists. However, it's not continuous. The fact that we have those two theorems, the reason that it fails because partial derivative with respect to x and with respect to y is not continuous here. So this theorem does not work. This theorem contrapositive and also work. This theorem works, but I mean the theorem doesn't work because it does not satisfy the condition of partial derivative being continuous. So we cannot use that theorem. And if it is not differentiable, it may not be continuous. Like I said, we cannot use this theorem because the condition is not satisfied. Like I said, a little bit advanced here. I'm just going to put here so we'll complete the section. Right, more sample. Right, let f of xy equal to that. find the partial derivative with respect to x and with respect to y. So derivative with respect to x. Now just more example. With respect to x, now we have two functions here. Only one of them have x in it. One of them has x in it, right? X squared. E to the y is a constant, so it's still constant. So we take derivative with respect to x. That is 2x. And e to the y is still a constant. So we don't do anything there. Next, y is a constant. Derivative of sine x is cosine x. So we only take derivative with respect to x because there is only one function of x. Once again, if there's x times e to the x, that's different story because x show up in two different functions. That has to be a product rule. This is not a product rule because we just have, we can still use product rule, but it's not necessary. It's only one function that has x in it. Take derivative. The other one is constant, so we stay. Yeah, so pretty much that. 2x e to the y cosine x. Right. And then we take derivative with respect to y. Once again, only one function that has y in it. The x squared is still constant. Should not do this. Right. As you see, the derivative, the part that we take derivative, I put in the parentheses to distinguish. Right, x squared is constant. We stay x squared. Derivative of e to the y is still e to the y. Derivative of y is going to be 1. Derivative of sine x with respect to y is still sine x. Right? Because with respect to y, sine x is a constant. So that constant will stay. Derivative of y with respect to y is 1. So that's what we have. So we just have x squared e to the y plus sine x. Right. Now, the Jacobian matrix, Jacobian, or just the Jacobian matrix is the matrix of partial derivative with respect to x and with respect to y. So we're going to put this in the matrix. This is the matrix, so don't put the comma in the middle. Just say 2x e to the y plus y cosine x and a space x squared e to the y plus sine x. So just put in the matrix, it's no big deal. But later on in terms of calculation, that will help. If we can think of this in more general sense, this would help if we put in the matrix form. Right. And that matrix of first partial derivative is called the Jacobian matrix. So Jacobian matrix is matrix of first derivative. And then later on we have the Hessian matrix, which is the matrix of second derivative. Right, second derivative. We already take the derivative with respect to x. Now we're going to take the derivative of x, that with respect to x again. The derivative of this with respect to x. With respect to x, there's once again there's only one x here, right? So the constant 2 will stay. Derivative of x is 1. The constant e to the y will stay. So that derivative with respect to x, constant will stay, constant will stay. Only one function of x, only one term has x in it. Take derivative of that. Next, y is constant with respect to x, right? Derivative of cosine of x, negative sine x. So that gives us 2e to the y minus y sine x. Right. Now derivative of x, fxy. So already take derivative with respect to x. Now we take derivative with respect to y. Now this term with respect to y, to x is constant. E with respect to y. Derivative of this with respect to y is 1. Cosine of x is a constant. So we just have 2x e to the y plus cosine of x. So that is, we used derivative with respect to x, and we have this 2. Now we're going to take derivative with respect to y, and we have to have fyx and fyy. Fyx, Claro theorem we did show earlier, mixed partial derivative should be the same. But that's a nice way to confirm that. So derivative with respect to y we already have done. So derivative of this with respect to y, with respect to x. The derivative of this with respect to x, derivative of x squared is 2x. E to the y is a constant. Derivative of sine x with respect to x is cosine x. So indeed, we have 2x e to the y plus cosine of x. The mixed partial derivative are equal. Now fyy, derivative with respect to y. We already did with respect to y. Now we still have x squared, derivative of e to the y is e to the y, and derivative of sine x with respect to y. There's no y there, right? Derivative of that with respect to y is 0. And once again, we can put in the matrix called the Hessian matrix of second derivative xx, xy, or yx doesn't matter because yx and xy are the same, and then yy. So the matrix of second derivative is going to be equal to 2e to y minus y sine x, 2x e to the y plus cosine x. Yeah, those two are the same, so kind of symmetric. So that is the Hessian matrix. Right. So far we have done the derivative for 2 variables. Now for 3, 4 doesn't matter. Still, just function. Right. Now, derivative with respect to x, we treat everything else as a constant. And whether we have 500 other variables, it doesn't matter. With respect to that variable, take derivative of that. Everything else we treat as a constant. Right. So first, I take derivative with respect to x. Look at this. That function x only show up at one place, so no need to use product rule. Right. If we have cosine of xz, different story. That is definitely product rule. But this is just z, so this is no product rule here. The x show up on the exponent though. So this is a chain rule. So I'm going to take the derivative of this with respect to x because that is a function that have x in it. So derivative with respect to x, exponential is going to be that, and derivative with respect to x. So that is derivative with respect to x. And then the cosine of z, that is constant. If we have a plus cosine z, that will be 0. Right? And I've mentioned this many times. Derivative of 2x, the 2 will just stay, the constant multiplier will stay. We take derivative of x. That is of course different than derivative of x plus 2. just take derivative of x, which is 1. Derivative of 2 is constant, 0. So that's different when it's add and then where there's multiply. Where there's multiply, where there's a constant multiply to it, we just have a constant multiply to it. So because we take derivative with respect to x, cosine of z is a constant. So cosine of z is the whole constant, just multiply to it. We don't do anything with the cosine of z, other than just carry on as the constant multipliers. We're going to take the derivative of that term with respect to x though, because it has x in it. So we have negative xy, negative xy. Right, so e to negative xy. Now we focus on the derivative. With respect to x, y is the constant. The negative is a constant multiplier. So the negative will stay there. The x derivative with respect to x is 1. And we have y is a constant multiplier. So it stay there. Constant multiplier will stay. And then we have cosine of z. So we'll have e to negative xy, negative y, cosine z, or we move the negative in front, e to negative xy, y, and cosine z. So that is derivative with respect to x. With respect to y will be similarly because we have one function of y here. But we do that for y. So e with respect to y. And then cosine z, constant multiplier, will stay. So still e to negative xy. Right. Derivative of this with respect to y. Derivative of with respect to y, x is a constant. So negative x still there. Derivative of y is 1. And cosine of z is constant, will stay there. So I have e to the negative xy, negative x, cosine z. So we'll have negative x e to the xy cosine z. Yeah, you can put the y in front or keep the y there or move the x here, it doesn't matter. And then next, derivative with respect to z. With respect to z, once again there's only one z here, no need to use product rule. So we have that e to negative xy. With respect to z, e to negative xy is a constant. Where we have the negative, constant multipliers, derivative we just copy down, right? Constant multipliers will not affect derivative, just write it down next to it. Derivative of cosine z though, we need to take derivative of that with respect to z, give us negative sine z. So we have negative sine z. Actually, let's say negative e to the negative xy sine z. Yeah, that better. Just write like that. Right. So whether we have 3 or even more variables, it doesn't matter. Derivative will be just like that. Yeah. Now we have an example here. It should be example 3, sorry. So the pressure and the volume and temperature, so those are 3 variables, P, V, and T. An ideal gas are related by this equation, PV, where K is a positive constant, depends on the amount of gas. Because in chemistry you will have something more precise than just a K there, but I said in math, that's a constant there, doesn't matter. PV equal to some constant times T. Right, now determine the rate of change of the pressure with respect to the volume. So we need to find, right, I just write what we need to find. Determine the rate of change of the pressure with respect to the volume. So first I'm going to show for pressure for P. If PV equal to KT, if I'm going to solve for P, the pressure is equal to KT over V. Or we can say P equal to KT V to -1. Right? Move from bottom to the top, change to negative. And then we'll take derivative with respect to the volume. So we write, by the way, in the next section there's a different way to do this. So we take derivative of pressure with respect to volume. So we're going to have KT, that constant with respect to V. Derivative of V with respect to -1 is negative V to -2. So that gives us negative KT V to -2. Or we move it down and we have negative KT over V squared. Right, so what do we have here? So what we have here is K is a constant, positive constant. T is the temperature. But in this formula, I just want one more thing we need to worry about. The temperature here is not measured in Fahrenheit or Celsius, where it can be negative. The temperature here is the measured in Kelvin. So absolute temperature cannot be negative. So that is absolute temperature. So that T is not going to be negative. So we have positive, 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 and negative. So we have pressure with respect to volume is going to be negative. What does that mean? What does it mean if it is derivative is negative? That means the rate of change is negative, right? Meaning one of them increase, the other one is decrease. So if we look at this, if the volume increases, the pressure will decreases when we treat T as a constant. So that's what we can get out of this. Because the derivative is negative, rate of change is negative, meaning one increase, the other one will increase. Volume decreases, volume will increase. Volume increases, pressure will decrease. So I just said, which means if the volume increase, then the pressure will decrease. Right. Of course, we don't even need to that. Look at the equation, we can pretty much tell that. Now next, let's determine the rate of change of the pressure. So we still have pressure with respect to temperature. So we still have PV equal to KT. So P equal to KT over V, or KT V to -1. Exactly what we had before. But this time we take derivative of pressure with respect to temperature. With respect to T, K is constant. Constant multiplier will stay. T, derivative of T is 1. With respect to T. V to -1, that is constant. V to -1 is constant. Constant will stay. So we just have K V to -1. So K over V. It is positive. K is positive. V volume is positive. Now, derivative is positive, meaning that if temperature increases, then the pressure will increases because derivative is positive. Right? So by that equation, well, I said, just look at the equation, we can tell that also. If V we treat as a constant, increasing the temperature, the pressure will increase. Just like the pressure cooker, for example. The pressure cooker has the same volume, right? But if you increase the temperature, the pressure will increase. So that is this case. Now, Let's look at the example here. Pressure and volume. If we keep the temperature at constant, if the volume increases, the pressure decreases. So if we have the same thing, let's say a balloon, right? If we increase the pressure, if we blow more air into it, no, that didn't work. Sorry, that bad example. Right, constant temperature, volume increases, the pressure will decreases. So if we have this, see, we have the piston, the same amount of air. If we increase the volume by pulling the piston, the pressure inside will decreases. If we keep the constant temperature, if we move this out, the volume increases. The pressure of the same amount of air, of course, will be less. So that one also obvious. But anyway, what we focus here, of course, is just the partial derivative. So when we take the bottom line of the partial derivative is, when we have partial derivative, we will treat every other variable as constant, right? So with respect to x, everything else is constant. Doesn't matter how many variables we have. It's always like that. Right. So that is partial derivative. From here to the end of the semester, we're going to use a lot of this. So there will be a lot of practice in the remaining of the class. So I'm going to stop here for this section. As always, thank you for watching.